Hello, everybody. This is the first in a series of videos on reasoning and proofs, and it's going to start with types of reasoning. Okay, first we're going to think about our logic, and we're going to do what's intuitive, right? What naturally comes to us. Before we get into the deep theory, let's just see what we can do naturally. So if you look at this pattern, square, circle, star, square, circle, what comes next? Star. Okay, here we've got kiwi fruit, otherwise known as Chinese gooseberry, and we've got some lovely tasty grapes here. So kiwi, grapes, grapes, kiwi, grapes, grapes, kiwi. Right, nice and obvious. Okay, so what about, let's do the same with numbers, because we're into math, so that's all about numbers. Not. Here we go. What comes next? 10. What comes next? 333, 333, 3,333, 33,333. Okay, what comes next? 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Square numbers. Okay, what about here? What comes next? Well, you got one box here, you got 4 boxes here, you got, or it's 2 by 2, here is 3 by 3, here is 4 by 4, so here it's going to be 5 by 5. And we can think of that in terms of boxes, in terms of area, in terms of perimeter. You see the number of boxes and the area goes up according to square numbers. The perimeter, we're adding 4 each time. There's interesting patterns here. You can see a logical pattern developing. Okay, now that's what we've done without even thinking about any theories or stuff. So let's start thinking about the theories. What we've actually just been doing is called inductive reasoning, because we looked at specific examples and arrived at a conclusion. That conclusion we call a conjecture, and we'll talk about why it's a conjecture a little bit later on. You've probably may have heard the word inductive before, and you may have heard the word deductive before. And they're not opposites, but they're complements. They're a different type of reasoning. It's called deductive reasoning, where you're taking a general rule and applying it to specific situations. So inductive is very much a scientific approach. Deductive is more the mathematical approach, but you'll see more about this in a minute. So just to reiterate, inductive uses patterns to arrive at a conclusion or a conjecture. Deductive uses rules, definitions, and properties to arrive at the conclusion. So inductive, we start with observing specific examples and generate a general rule. Deductive, we have a general rule already and we apply it to the certain situation. Let me give you a bunch of examples, but before that, think about this question: which is better? Well, actually we need both. All right, in science and social sciences, you'll use inductive reasoning a lot. In mathematics, you use deductive reasoning a lot. In the arts, you'll use both a lot. Okay, and they are both applicable in different situations at different times. Here's some good examples. All right, here's an example of inductive. I've done 2 tests. The last 2 tests were easy, so the third test coming up, it'll be easy too. All right, I've spotted a pattern. I've applied that pattern to my conclusion. Deductive, there is a rule in the handbook that says there will be a test every quarter. So I'm currently in the middle of a quarter, so there will be a test at the end of it. Okay. Inductive, here's a pattern. What comes next? 10, 5, 2.5. So looks like we're halving everything, so we'll half 2.5 is 1.25, then 0.625, etc. Okay, so we see a rule and then apply it. This way, they give us the rule, and then we apply it. So starting at 10, 20, 40, 80, 160. Okay. Here we've got 3 triangles, and they're connected. So the first 2 triangles up here are right angle triangles. This is 90 degrees in here. Is this one 90 degrees as well? Well, inductive logic would tell me yes, because 3, 4, 5, well, double that, you get 6, 8, 10. Double it again, you get 12, 16, 20. Or multiply this one by 4, you get 12, 16, 20. So there's the same ratio of sides. So if there's the same ratio of sides, the angles will be the same. So yes, it will be 92. If these are 90 degrees, if these are right angled, this will be right angled. Deductive logic says there's a rule called Pythagoras' theorem that talks about right angled triangles. A squared plus b squared equals c squared. So let's check it out here. 12 squared plus 16 squared equals 400. 20 squared is 400. Yes, it's the same. So we can show this is a right angled triangle by deductive or inductive logic. And they're both equally as valid. What's the problem with inductive reasoning though? How many examples do you need before you can make your conjecture? Alright, in the pattern of numbers, if I go 5, 10, what comes next? Is there enough information? Probably not. How many do you need to make your conjecture? And this comes back to this famous example of all swans are white. Back in maybe 200 years ago, scientists in Europe would suggest that all swans are white. Then they went to Australia and discovered there were black swans, and that totally disrupted their taxonomy of biology. Yes. Well, how do we define a swan? It's a white bird. No, it's not, because there's black swans. All right. So this is why when you're doing science, you're probably not coming to conclusions as much as conjectures. All right, it's something you can say with some confidence, but you need to be open to changes. So now instead of saying all swans are white, scientists will say all swans we know of on Earth are either black or white, suggesting there could be swans on Earth we haven't found yet, or swans on other planets that are different colors. Okay. What about deductive reasons? Are there problems with that? Yeah, there's quite a few problems actually. If your initial premise is wrong, your conclusion's wrong. So Australians are good swimmers. People generally think that's true. I'm Australian, therefore I must be a good swimmer. Well, tell you what, I am a good sinker. I do not swim very well. So one exception makes the rule wrong. I'm the exception. Therefore this is wrong. Therefore my conclusion is wrong. Okay. The other thing is that the universe is messy and doesn't always follow the rules neatly. For example, mathematicians say parallel lines go on forever and never meet. Well, that's not really true, because they're not going to be straight lines forever and ever, because the world is round and space is curved. However, believing that they are go on forever and never meet helps us do a lot of analysis of angles and other things like that. That is true and useful. So even though this assumption is not real, it's ideal rather than real, believing it helps us analyze and make useful conclusions. We call this an axiomatic system. This might not be true, but let's assume it to be true, and then we can do a lot with it. if you want to really study the philosophy of mathematics, look up Gödel's incompleteness theorem, and he'll discuss this a lot with you. Alright, I've given you a lot to think about there. Now it's time to practice. Your teacher will have some questions for you, I am sure.